Right, question 18 then. So I have got a diphenol here, and I'm doing a Fiedel-Crafts reaction to pop on this alkyl group here. I obtain a very low yield of E, but a higher yield of a different organic product. Suggest an identity for it. Okay, well this, remember, it's a diphenol, so it's going to be even more reactive than phenol in terms of electrophilic substitution. So I probably di-substituted because I've got 14 carbons, whereas here I've got 10 carbons. So I put 2 groups of this on, so it looks like a really dodgy benzene ring, but that's one, and then I've got another one like so. Okay, so it says I don't need the iron trichloride catalyst because quinol is more reactive than benzene. Why is the students very incorrect? Well, we need to talk about the reactivity of phenol here. And remember, in phenol, you've got a lone pair of electrons on the oxygen atom. This is partially delocalized into the benzene ring, making it more susceptible to electrophilic attack. And that's pretty much it, really. Okay, so part B then, a bit more chemistry involving benzene. Lost the phenol group, but I have got to look at this synthetic route here. So again, identify what has changed. So this part has not changed. The only thing that I've introduced is this guy here. So whereas I had a carboxylic acid before, I now have an ester. So how do you make an ester? Well, you need concentrated sulfuric acid as your catalyst, and you are going to introduce this alcohol here, which is of course ethanol. Okay, in this next step, it wants me to reduce this nitro group down by using tin and concentrated hydrochloric acid. So, write an equation. Now remember that when I represent the reducing agent, I do a square bracket H, and I need 6 of these for this reaction to give me the product required, which has changed my NO2 group into an NH2 group, like so, and I also make 2 water molecules as well. Okay, so now we're going to move on to question 19, and we are going to look at synthetic routes of an alpha hydroxy acid, which is shown here. And I'll draw them out so you can see them a little bit clearer. The first thing I'm going to do is I'm going to react this, do reaction 1. Look at the conditions. I'm adding a carboxylic acid here and sulfuric acid, and therefore that looks like an ester reaction. The ester, I've got a nice alcohol there, so it is going to add across there. So let's do that one first of all. I'm going to have CH3, CH2 twice, and then this group will remain the same, but on the alcohol there, I'm going to add this carboxylic acid like so. For reaction 2, I am adding sodium bromide with sulfuric acid. So that is a substitution reaction in which I'm going to substitute that OH group with a bromine atom. So again, it's going to be CH3, CH2 twice, and then now, rather than an OH there, it's going to have a bromine atom like so, but the carboxylic acid remains unchanged. Okay, the next question, part 2, it wants me to name compound G. So compound G, let's look at it. So I've got 1, 2, 3, 4, 5 carbon atoms. So it's going to be pent. I've got a double bond coming off carbon number 2, so it's going to be pen-2-ene, and then it's a carboxylic acid, so it's going to be oic acid for your carboxylic acid here. Remember, in a carboxylic acid, that's going to be carbon number 1. And now, because I've got a double bond, I need to see whether it's an E or Z isomer. Your two highest priority groups are going to be that one and that one. Therefore, they are opposite sides of each other, and therefore it is the E isomer. So it is E-pent-2-ene oic acid. Well, I'm going to keep this one up. It wants me to now draw compound H, which is an isomer of compound G. So I'm going to draw the Z isomer now. So I'm going to move my two hydrogens down below, and then this will be CH2, CH3, like so. So I've just swapped those two around. And then the next step is it wants me to draw the repeat unit of the additional formula that can be formed from compound H. So basically what you're going to do is you're going to remove this double bond. So let's do that. I'm going to do it on this one. So remove that one. Not like that. Let's try again. Doesn't want me to remove it. Like so. And then you are going to just extend that there and there. And that gives your repeat unit of the addition polymer. For part 4, it says the addition polymer that we've just drawn can be used in industry, and we're trying to process waste polymers in a more sustainable way. Apart from recycling, 2 methods for usefully processing waste polymers, where you can combust them. You can't just say combust, you combust them for energy production, and the other one is you can use them as an organic feedstock for the production of plastics as well. Right, joy of joy, it is now another synthetic route. So I have got to go through step 1, step 2, state a suitable oxidization for step 1. Okay, so this is quite easy, but let's draw up propane 1,2-diol. So propane 1,2-diol is going to look like this. First of all, suitable oxidization, that is going to be potassium dichromate, so K2, Cr2O7, and it is going to be acidified as well. Write an equation for step 1. So this is where you've got to be a little bit careful. So I'll draw it out again. You've got your propane 1,2-diol, like so. Now, you are going to oxidize this to a carboxylic acid, so that's going to take 2 oxygens. You're going to oxidize that to the ketone group there, so that's another one. So you've got to add 3 square bracket O's to that. That is then going to give you your product, like so. But it will also give you 2 water molecules to balance out the equation. Many people forget the water molecules. Outline the mechanism for step 2. So the acid remains the same, but your carbonyl group here gets oxidized to my secondary alcohol there. So let's draw this out. So CH3, C double bond O. I'm just going to draw my acid group like that. Your nucleophile is H minus. You've got delta plus, delta minus on your carbonyl group like so. That goes there to break my double bond to give me the intermediate CH3, CO minus, H, carb, oxalic acid group remains unchanged. Pop a lone pair on that. You've got an H plus knocking around, so the electron pair just go there to give you your product. Okay, so now it wants the dot and cross diagram of sodium borohydride. So, Na plus is quite straightforward. You don't need, you can just do that. It's lost its outer shell of electron. The BH4 is slightly more difficult. Boron, as you will know, is in group 3. Like so. That's a bit of a dodgy diagram there, so let's just sort that out. Okay, so I've got an overlap there and an overlap there. So let's do 3 normal boron hydrogen covalent bonds like so. Now this other hydrogen is also donating an electron to that as well, but it's BH4 minus like so. So I'm going to use a triangle to represent the minus on the other electron being added in like so. The full electronic configuration of the sodium plus, 1s2, 2s2, 2p6, because it's lost its outermost electron. Right, so this is quite an interesting one. You're going to have to make, got to go with it really. Make an assumption, then realise that doesn't work before you can get the right answer. So, okay, let's give it a go. So I've got 4 compounds, and I need to identify which one I have, which is compound K. So the first thing you would do, if in doubt, work out moles. What can I work out the number of moles for? Well, I can work out the number of moles of sodium hydroxide, because I've got a concentration and a volume. So moles of NaOH is going to be the volume times your concentration over 1,000, and that comes to 2.82 times 10 to the minus 3 moles. Right, so let's assume it's a one-to-one reaction. Okay, so assume it's a one-to-one reaction. If we do that, then the moles of K will be the same. And that, moles of K is going to be 2.82 times 10 to the minus 3, and that is in 25 centimetres cubed. However, originally it was in 250, so in 250 it's going to be 2.82 times 10 to the minus 2. I know how much I dissolved, so I can work out the molar mass. The molar mass is mass over moles, so it's going to be 1.89 divided by 2.82 times 10 to the minus 2, and that comes to 67. Right, straightforward so far. Then you start working these out and you realise that the smallest one actually has a molar mass of 76. Malic acid is actually 134, which you notice is exactly half of 67. And therefore it can't have been a one-to-one reaction, it must have been a one-to-two reaction, in which case if you run through the calculation again on a one-to-two reaction, you will find the molar mass as being 134, and therefore K is malic acid.